Welcome back, everyone. For the last talk of this afternoon section, you have Jon Chaika who will be talking about simple distribution.
Okay, thank you very much. So this is my last lecture. I took a little break from the sort of absurdity I was doing for my first 3 lectures this week, where I have been doing hard proofs of an easy result in order to suggest the arguments for easier proofs of hard results. And I took a brief break to prove the mixing with respect to Lebesgue measure of this map A given by 2, 1, 1, 1. So let's remember our context. We have the square torus r squared mod z squared, the integers mod the reals mod the integer, the real squared. And our matrix gives a map of this to itself. And it's got 2 eigendirections. It's a symmetric matrix. They're orthogonal to each other. 1 plus the square root of 5 over 2, 1. And 1 minus 1 minus the square root of 5 over 2. They have corresponding eigenvalues, 3 plus the square root of 5 over 2, and 3 minus the square root of 5 over 2. For any vector, and I'm going to this lecture be considering this vector, the contracted one again, we have that you can define the flow on the torus by just adding t times that vector in the group. This is a perfectly good abelian group. You have an addition in this group. In a mild abuse of notation, one can denote it by plus. So you just add t times the vector, and that defines a very nice flow on this. Just for to remind you of what we did 2 lectures ago, we showed that for any v that's not a periodic direction, the flow in this direction is uniquely ergodic with respect to a little bit measure coming from a Lebesgue measure. In last lecture, we showed that this map is ergodic, is mixing with respect to the measure coming from the area. But we didn't prove that it was uniquely ergodic. This map was uniquely ergodic, and that's good because it's not. So today we're going to do our last argument where we take advantage of the contracting and expanding dynamics of A to prove ergodicity of very special flow, unique ergodicity of very special flows like this, using an argument due to Dani, which will use the mixing of this flow. Okay, so theorem. If V is equal to 1 minus 1 minus the square root of 5 over 2, the contracted direction for A, then F the T V has a unique invariant probability measure let's just recall that my flow is an isometry, so it preserves the measure coming from the area. So we know what this one is. It's Lebesgue. As I've said probably 17 times at this point, there's only one guy. We know one guy. They gotta be the same. Okay? Now, if you guys might remember, once again, I think a handful of times already, we have a criterion for this, which is, proposition it suffices to show that for any G, 1 Lipschitz, and P in the torus. And that the integral from 1 over T of G of F to the T sub V of P minus the integral of G d lambda goes to 0. Everybody happy about that? Okay. All right, so this proof uses the mixing. So recall from last lecture. 10:45 today. R squared mod z squared to itself is mixing with respect to lambda. Everybody happy about this? Okay, so now I want to prove the sufficient condition taking advantage of the fact that my flow is mixing. Okay. And so let's talk about a schematic of how this proof is going to go. And then I'm going to go present the details with some care, but it'll seem a little artificial if we don't do this. So what's the picture going to be? I have some very long flow trajectory. Okay, and it keeps going, so I'm just going to stop there rather than draw it forever. And so as we've done before, I want to apply a to the k to this to make it of reasonable size, but based at a different point. I'm going to ignore the issue about the fact that the point is moving, and I'll justify why that doesn't wreck everything for me at the end of it. But just pay attention that the point is moving, and now it's just going to be some kind of reasonable piece here. So I choose how big k is to shrink whatever long flow trajectory I had to a small size, say epsilon. Everybody okay with that? Now what I do is I fatten my box up. I've got two colors. Please tell me if yellow doesn't show up very well. I fatten my box up a little bit in the expanded direction for A, which is the contracted direction for A to the minus K. I've got these lines here. Can you guys see that yellow is different than white? Okay. Let's try something different. Can you guys see that orange is different from white? Okay, maybe one person changed their mind and it's unclear how. Okay, so now what I do is I flow backwards. I reinterpret this picture I had here. I have extreme contraction, so my orange lines are almost directly on top of this. All of my orange lines are here. Okay, everybody happy about that picture? But because I'm mixing, what I have is I have that a to the minus k. Yeah, so because I'm mixing, what do I have? I have that if I give this rectangle a name r, and I look at the integral of the characteristic function of r, composed with a to the minus k, and then this is pointwise multiplication. I multiply this by f, and I multiply it by d lambda. This is going to converge to the Lebesgue measure of R times the integral, sorry, my F should be a G. The integral of G d lambda as k goes to infinity. So if my segment was extremely long, my k would be extremely big, and this would be extremely close to the integral there. Everybody happy? But if you look at the image of my rectangle, so my rectangle, a to the kr, a to the minus kr, basically is lines, is the union for 0 less than or equal to s less than or equal to l of f to the s of p. I've contracted in the other direction. These lines are almost on top of each other, so it's basically a constant that's just this object. Okay? So then that gives me that the integral from 0 to L of 1 over L of G of F to the S of P ds is roughly equal to the integral of G d lambda. What happens to this factor coming from the rectangle? How many segments do I have basically like this? That's coming from the area of the rectangle. Okay, everybody happy about this? There's a transverse direction and there's the direction, the flow direction. So the 1 over L is giving you, is coming from normalizing for the flow direction. Then you've got another term coming from the transverse direction, and that's getting the multiplicity of these objects. All right, that's the idea of the proof. Does anybody want to ask any questions on the idea? Okay, let's go through the details because I think that'll help make the ideas be crystallized. Okay, so let's make a statement. So we have the following lemma. So lemma: if there exists a point P in my torus r mod z squared, sorry, r squared mod z squared, L, think of this as a large real number, 1/4 bigger than epsilon, bigger than 0, and G, 1 Lipschitz. So that 1 over L, let's try that again, 1 over L times the integral from 0 to L of G of F to the T of P times minus the integral of G d lambda is greater than 2 epsilon, then there exists a rectangle this R. I'm going to tell you this rectangle R with one side epsilon length epsilon, another between 3 plus the square root of 5 over 2 inverse and 1. A k in the natural numbers, so that if I look at the absolute value of the integral of the characteristic function of r, composed with a to the minus k times g minus the integral of r, let's say Lebesgue measure of r, times the integral of g with respect to Lebesgue measure. Okay. This will be greater than epsilon. Sorry to erase your flower. This will be greater than epsilon. So my 2 epsilon, I've given up a little bit, and it's bigger than epsilon, but this will contradict the mixing of A inverse. And moreover, k goes to infinity without. K will be determined by a formula coming from L, and it goes to infinity without. Okay? Everybody happy about this? Okay? So let's go through what the picture is. I'm going to tell you how to build this R. Okay? And then we're going to carefully look at the estimates here, and we're going to relate we're going to go in sort of the other direction to the way I presented it, which is we're going to estimate this correlation by this integral. Okay, so it's sort of, this has happened a couple of times. Sort of the conception you should have in the mind goes the opposite direction for sort of a reasonable way of writing a proof, or at least the way that was reasonable to me. Other remarks. Oh, I mentioned the moving of the base point of objects. This rectangle depends on k. So just something to be a little bit careful about. So we'll need to address that at the end of the argument. But as stated, the lemma is true. And the proof is basically the picture you saw. Okay, so I need to tell you how to make J. It probably isn't all that surprising what J should be. Let J be equal to the logarithm of L. I want to do ceiling function of the logarithm of L divided by 3 plus the square root of 5 over 2. Okay, so that's going to be my I'm sorry. This is going to be my K. Sorry about this. It's going to be my K. Everyone happy about that? Okay. Observe. The union from 0 less than or equal to S less than or equal to L of F to the S of P. I'm going to suppress my V's if everybody's okay with that in the subscript of my flow direction. I'm going to apply A to the J of this. Has length between three plus the square root of 5 over 2 inverse and 1. That's why I chose K. That's why I chose K to be what K is. Right, that's exactly the number to choose for this circumstance. Okay. All right, so now what I want to do, I want to let R be the rectangle. With one side A to the K union 0 less than or equal to S less than or equal to L of F to the S of P. By the way, is it clear to everybody what I mean by this set multiplied by this? That this is a set, I'm multiplying it by this matrix, what that is? Great. And the fact that it's contracting is once again just this property that when I multiply A by this matrix, I shrink things by this amount. I guess I'm using that the reciprocal of 3 plus the square root of 5 over 2 is 3 minus the square root of 5 over 2. Okay, okay, so that's this. And the other side, a segment of length epsilon. Can anyone guess what direction it's going to be in? Anybody want to take a guess? Yeah, the other one. And it's a good idea to make it the other one. Let's just take a moment to sort of collect ourselves and look at this picture. Why on earth would I want to make it the other one? Well, epsilon isn't big. It's, you know, who knows what's going to happen to it when I apply A? Well, if I choose it in one of the eigendirections, everyone knows what's going to happen to it. And in particular, if it's in the expanded direction for A, it will be contracted by a to the minus k, and that will be the engine to make everything collapse onto the direction, onto the flow orbit. Everybody happy about this? We've sort of seen this argument, or versions of this, sort of a few times already, especially in the lectures yesterday. Okay, so that's my rectangle R, and now I'm basically in business. So observe, R is foliated. R is the union from 0 less than or equal to, let's call this script L or backslash ELL in LaTeX. Script L less than or equal to epsilon. And then I'll take the union from 0 less than or equal to S less than or equal to T. And then what will I do? I'll be looking at nope. I'll want to put an A to the K here of S to the L of F of S to the P. And then to this whole thing, what am I going to add? I'm going to be adding L times 1 plus the square root of 5 over 2. Okay, so this is a double union. Okay, and I'm adding this piece and the other thing. And that's what L is, just in coordinates. Okay. But you should just say all I'm doing is I'm parametrizing these segments here, and I'm going to prove that each and every one of them is very close to this piece, and so their integral of G is going to be very close because G is 1 Lipschitz, as we've seen a bunch of times. Okay. All right, so now A to the J of R is going to be equal to the union and let's look at what's on the inside. On the inside, it's just the union from 0 less than or equal to S less than or equal to L of F of the S of P. Okay, I have, I'm lying to you, this is A to the minus K of R. I'm now applying my A to the minus K to go back. All right, so I've killed off the A to the K and I just had the guy I wanted, the guy I understand a little bit about. It's bad for averages. That's all I sort of understand about it. And then what's going to happen to these other pieces, I'm going to be adding to this 3 plus the square root of 5 over 2 to the minus k is L times 1 plus the square root of 5 over 2 and 1. I'm sorry, I made a typo here. This was a vector, not a number. Okay, maybe people already understood that. Sorry about that mistake. And once again, I'm going to take the union from 0 less than or equal to L less than or equal to epsilon. And this is the expression I have. But observe, this is microscopic over here. And in particular, it's smaller than epsilon. Okay, so now what I can do is I can look at the integral of the characteristic function of R composed with a to the minus k times g d lambda. Okay, and what's this going to be? This is going to also be the integral from, let's write it this way, it's the integral over a to the minus k of r of g d lambda. That's kind of what that means. Everyone happy about this? Okay, and by Fubini's theorem, this is equal to the integral. Well, let's do the inside integral first. This is going to be the integral from 0 to L of g of f to the t of p, okay, dt. I'm going to take the integral from 0 to epsilon times 3 plus the square root of 5 over 2 to the minus k of plus L dl. This is not d lambda, this is dt. L times 1 plus the square root of 5 over 2, 1. Okay. And then I want to divide by the area of the rectangle. Times 1 over. Maybe actually I don't want to do that. Okay, yeah, I think that's correct. All right.
DL.
Thank you, D. Thank you. Everybody happy about this? Now this term is equal to g of f to the t of p plus a constant that's not bigger than L times the length of the vector 1 plus the square root of 5 over 2, 1. That's just because this is 1 Lipschitz, okay? And in particular, this term is an absolute value less than or equal to 1. Less than or equal to epsilon, less than epsilon. Everybody happy about this? Okay. And so from this, I've established this statement.
Sorry, John.
Yes.
In the first line, if you want to integrate over a minus k r, shouldn't you actually compose chi with a plus k? Because then a of k of x belongs to r. So
Yeah, I
x
think you're
belongs
right.
to A
Yeah, I think you're right.
R.
Yeah. So, yeah, sorry about this. I'm just going to leave it like this at this stage. There's no way I'll get this right, okay? Okay, but I think everybody gets the idea. Okay, and so we have the lemma. Okay. Any other questions? So now we're essentially done. So there's just one problem. So just notice there's one subtlety we're missing. The k is going to infinity, but our rectangle is changing. So our power k is going to infinity, but our rectangle is changing. Everyone happy about this? So what I'd like to do is I would like to say, I've got a fixed rectangle. Notice the word fixed here. I'm taking powers of k going to infinity, and I'm getting that my correlations aren't going to 0. That violates mixing. Okay? Now, however, we can pass to a limit. We can pass to a subsequence. rectangles are a subsequence K sub j, so that I want to make the dependence clear on my rectangles here so that it makes sense, so that my R sub K sub j converge to a rectangle. Moreover, of positive area, with bounded dimensions. In dimensions, I just mean width and height. That's what I mean by dimensions in this statement. Everybody happy about this? And in particular, they're bounded away from 0 and infinity. Okay? And so then the claim is that if R to the K sub j converge to R to the K, let's say R. Well, let's call it R tilde. And the integral over R sub K to the j of G d lambda minus the Lebesgue measure of R times the integral of G d lambda is greater than epsilon. Let's put a K sub j here, K sub j here, for all K sub j, then the same thing is true for R. Let's put an A to the K sub, sorry, I left out my A to the K sub j here, A to the K of R sub K sub j. Here I have an A to the K sub j of R. Now here's the limiting guy, R tilde. I'm once again doing G d lambda minus lambda of R tilde, integral of G d lambda. And I'm taking the limit as J goes to infinity. And this is bigger than or equal to epsilon. Okay, so that's my claim. So now these rectangles are extremely close to each other, but this map I'm having is extremely chaotic. So why is this true? It's true because you consider the intersection of A to the K sub j of R tilde and, of R tilde and R sub K sub j, and on that you have perfect equality on their intersection. And their symmetric difference has measure going to 0 and you bound trivially. Everybody happy about that? These are L2 estimates, it's just sort of more like an L infinity estimate, or an L1 estimate. Everyone happy? L1 plus L infinity estimate. Everyone happy about that? Should I write that detail out? Okay, great. Okay, so that completes the proof. Any questions on this argument that's due to Dani? So at this stage, I want to recall the three arguments we've done to prove ergodicity of this flow or in its orthogonal direction and sort of put them into a little bit of a context. Okay. So Davida said that I was going to prove the unique ergodicity of the Horus cycle flow in his setting, and I've somehow deliberately avoided doing that. So now I want to do it. I told Davida I was going to do it, so he's completely fine to be upset and angry, and you can tell he's very much. So I want to now connect it and to say a few words about how the arguments would go in this situation. Okay. So our arguments work very nicely. Work well. for f to the t, which say could be given by 1 t 0 1 or 1 0 s 1 on SL2R quotienting on the left by gamma, if gamma is a co-compact lattice, if gamma is a lattice, and it might be a not co-compact lattice, and at each stage I'll say a few remarks on the non-co-compact case. Okay. So when this space has finite volume, but it's not a compact space. Okay. So let's make some remarks. We have, and A is replaced by e to the t. I guess you had them over twos, right, Davida? You had your t's over two? Okay, great. In this case, we have an expanded direction. Well, let's give this a name, let's call it. We have an expanded direction. An expanded and contracted direction. And so we make this a GT expanded direction and a GT contracted direction. So GT expands a direction and contracts a direction, meaning it preserves that direction and contracts the orbits along it in one of them and expands them in the other direction. And these are these two directions. So I think because of the way you're acting, this guy's the expanded guy and this guy's the contracted guy. If you acted on the other side, it would be the other way around. Everyone happy about this? Unfortunately, so 4x4 matrices are R to the 4. Determinant 1 is a one-dimensional condition. This is a three-dimensional space, modding out by something discrete, still 3 dimensions. I've given you 1, 2 directions. There's one more direction. There is also a central direction. Given by the flow. So this never showed up in my arguments, this central direction. And let me say a little bit what I mean. I mean something very precise. So let's assume that I'm in the co-compact setting, so my injectivity radius is bounded from below, away from 0 everywhere. So then I can look at a point in my space, and I can look at its distance. So these are 2 points in my space that I've flown forward, and this is the same as the distance of the initial points. So what am I doing? So let me talk a little bit about the geometric picture. I've got a base point here. If I was to move in either of these 2 directions, I would have expansion or contraction in the appropriate directions for the geodesic, for this GT flow. But I move instead in the flow direction itself just a little bit, and I get this point. Everyone happy about that? Okay. Now, I flow this whole picture forward. Everything was about how distances changed as you flow forward, whether it's contracted or whether it's expanded. Delightfully, this direction is preserved. That's wonderful. But unfortunately, the distance isn't contracted. Oh, that would have been great. It's also not expanded. That would also be okay. Maybe I could contract in the other direction, but it just stays the same the entire time. Everyone happy about that? That has never shown up in the arguments I've done. So Codene's argument goes through just fine. The first argument goes through phi. And so the moral you should say is that the central direction has no effect on equicontinuity. No effect on equicontinuity. If you start close enough in the central direction to the point you started at, as you move forward, you still stay very close in the central direction to the point that your sort of the moving averages look at. So you still stay wonderfully continuous. This uniform continuity goes through perfectly wonderfully. Everyone happy about this? Okay. Now there is something that I did mention in the Codene argument case.
So I have a very general question. So I don't follow what is the aim now. So now you assume that basic flow is mixing and you would like to.
I am doing a twofold thing. I'm recapping the arguments I did and trying to say a little bit about how they kind of sit in comparison to themselves. So that could be done without the geodesic flow. But then the other aim I have is to connect this to the setting of the geodesic flow and say, what do you need to do if you are doing what I was supposed to do and you're moving these arguments into the setting of SL2R? What are the complications and how do you overcome them? Did that answer your question?
Yes, but you said central direction has no effect on equicontinuity.
Yeah, so should I recall Codene's argument quickly?
Yeah. I think
okay, so Codene's argument is, if you remember, we had these averaging operators, phi sub k, which are equal to the integral from 0 to 1 of g of a to the k of f to the t 1 plus the square root of 5 over 2, 1. It's the expanded direction in this case, A, comma, B. And we proved that the phi sub k's were an equicontinuous family because in the flow direction where we had expansion, if you remember there was this scary thing and I kept pointing out how it was scary, but the average took care of it in that direction. The average took care of that. The average takes care of it in the expanded direction also. In the other direction, we had contraction, which made the distance element really easy, but you just need that it's not growing in order to get the equicontinuity. You didn't actually need that it was going to 0, you just needed that small things stayed small. Small distances stayed small. Did that answer your question? Okay. So does it make sense that central direction has no effect on the equicontinuity? It's of these phi sub k's. Do you want to ask a follow-up question or have me?
No.
Okay, great, cool.
This is just by definition of
Yes.
these guys.
Yes. Okay, now in the non-compact setting, so we wanted to pass to a limit. We can still get a limit. Still get sequential limits. Okay, but here's a big but. But to relate the integral from 0 to, let's say, a particular L of g of f to the s of p ds to phi sub k of something, okay, I need to fill this in. This needs to be a to the minus k of p for appropriate choice of minus k. Okay, everyone okay with it? It's basically the choice of k I had beforehand. You want to contract it so it's reasonable, and then you can relate these along a subsequence of L's, and that's how you relate them. So you need this guy's going to a limit, okay? So what you need is you need that P does not leave compact sets. You need that it has a subsequential limit point. That a to the minus k of P has a subsequential limit point. Now on the torus, that's an absurd condition, but in SL2R mod SL2Z, for example, that's a meaningful condition. Okay, you need to, okay. Any questions on sort of Codene's argument? Maybe I'll just say one last slogan. Codene's argument sort of has sort of the minimal input. You just need a little bit of topological information and you're sort of in business to run his argument. Now the next argument, so this, what I call the Ratner-Masur argument, okay, the central direction actually is a little bit problematic. Okay, because I can't really perfectly match points. If 2 points differ in the central direction, which is typical, by using my flow operations, I can't bring them closer together. They just stay that distance apart. Everyone happy about that? Okay, so nevertheless, Ratner's paper, you can look at it. Has anyone looked at Ratner's paper on the notes? Okay, sorry for that quiz. It's about the ergodicity of the horocycle flow, or the unique ergodicity about the horocycle flow, not just on SL2R mod a co-compact quotient, but on SL2R mod SL2Z. So what's going on here? So what it does do nicely is it upgrades from ergodicity to sort of measure classification. It is helpful for upgrading ergodicity to describing lots of equidistributing orbits, to giving criteria for orbits to equidistribute. Criteria for orbits to equidistribute. Okay, I'm in an ergodic situation, so plenty of orbits look pretty close to being equidistributed. So I pull them back and I ask what points will look like they're pretty close to being equidistributed when I push them forward. So I look at a point and I ask, what of these points, when I push them forward, will their long orbits be close to being equidistributed? Okay, if I start out, if the pullback of my point is close to one of these points by a small amount in the central direction, and a reasonable amount in the contracted direction, and something in the expanded direction, I can use the same exact trick, and I push them forward. I was super close in the central direction. I stay super close. That's the point of the central direction. The reasonable amount in the contracted direction goes down to being minuscule, and so these orbits are fellow traveling on a definite chunk. Bob's my uncle, and I can upgrade to, I can upgrade my ergodicity for criterion for orbits to equidistribute. For example, in the co-compact setting, I can get unique ergodicity, and in the non-co-compact setting, I can get equidistribution so long as my orbit returns infinitely often to a compact set under the direction of the flow that contracts the direction of my dynamics. Okay, so the name of the game is I contract my dynamics, and I wait until this contraction lands me in a compact set. I match in this compact set, and then I flow forward. And how do I match? I don't let myself go very far in the central direction, but I let myself go some epsilon. I let myself go 100 in the stable direction, and say 10 in the unstable direction, or also epsilon in the unstable direction, however you want to construct it. And then I flow that forward to the guy that I've matched. And once again, it's not a guy, what I'm matching with is guys that when pushed forward will be close to being equidistributed, not that are close to being equidistributed now. But this pulling back business preserves measure, and ergodicity gives me that these have almost full measure, so I can play this matching game, because I'm matching with a set of almost full measure. Did that make any sense? Let me see how I'm doing on time. Yeah, so maybe I'll leave it at that, and maybe I'll draw, so maybe actually I'll quickly draw a picture of this version of this argument to maybe make it make sense. Okay. So I've got my modular surface. I guess it looks something like this. Okay, right? And I've got my long horocycled orbit in here that I'm trying to understand, wrapping around in some complicated fashion. Okay, and what I'm doing is I'm now going to pull back under the geodesic flow so that it's just kind of a small segment. And what I want, that was a horrible picture. What I want, so now this is just a reasonably sized segment, and I want that it's in the compact part. I don't want it that it's far away. Okay? So now here I've got my set G, which will be equal to the set of points so that these to be contracted, so that 1 S 0 1 is almost equidistributed. In segments at e to the t. Okay, so that's the thing that's going to be shrunk to being size 1 by this. Now I'm pulling back G. So here I consider G minus T of G. Okay, and I want to match this guy with things in G minus T of G. Now this has almost full measure, so I can, so long as I'm in the compact part, there'll be a nearby guy. Okay, did that make a little bit more sense? Who's with me at this point? Okay, maybe I can answer questions later. Yeah. Okay, so let's talk a little bit more through this argument, because this is actually sort of adding content. Do people want to ask questions on sort of what's they're having trouble with understanding? Okay, is it clear what I mean by almost? Is anyone having trouble with what could it mean to be almost equidistributed? Okay, so we'll call. So what's G going to be equal to? G is going to be equal to the set of all x, so that for all G 1 Lipschitz, the integral from 0 to e to the t of G of e of G of u sub t, let's call it f to the t of x, dt minus the integral of G, e har. I want to divide by e to the t, and I want this to be less than epsilon. Okay, so it turns out that this set goes to full measure as e to the t goes to infinity. It's morally a consequence of the Birkhoff ergodic theorem, and that this is sort of a pre-compact, that this is a compact family in supremum norm. Okay, so we can call this G sub t, and it turns out that the limit of the Haar measure of G sub t goes to infinity. Goes to 1, goes to full measure, sorry, as t goes to infinity. Okay, so I don't want to match with G sub t here. I want to match with the pullback of G sub t, because I'm going to match here. But that's not going to really necessarily help me all that much. What's going to help me is the matching as I push back forward. And then these guys will all be sort of close to each other. The closeness will stay the same in the central direction. Since this had almost full measure, I could match by moving very little in the central, and in the contracted direction, it's contracted. Life gets better. Okay, who's with me at this stage? Okay, great. Thank you for... Okay, so now I just have a couple more minutes, and so I'll just say that Dani's argument goes through nicely. Today's argument goes through well. Nicely. And what's the only issue? I want to make sure so rectangles go to three-dimensional boxes. Three-dimensional boxes in these coordinates, because boxes in these coordinates that are small enough are sent to boxes in these coordinates that are small enough. And you want to make sure the central direction is small. Make sure central direction is small. But you fix an epsilon ahead of time, and based on that, you choose your central direction to be small. In the non-co-compact setting, as has shown up before, non-divergence plays an important role. So if you look at this, I didn't build my box here. I had to move my time. I used the dynamics to build my box, and then I moved backwards to sort of understand the picture. And I want that this piece is in the compact set. I want the base point here to be in the compact set when I'm building my rectangle. Okay? And the reason is because there's a lot of reasons. One is passing to the limit, but also I can't build a rectangle of definite size if the injectivity radius is collapsing. For example, if I'm running out this cusp. Okay. In the case of the SL2R mod SL2Z, basically for the argument I gave when I was generalizing the Ratner-Masur argument to irrational rotations, unless your element of SL2R mod SL2Z, which corresponds to a lattice in R2, so something like Z squared, a discrete two-dimensional closed subgroup. Unless that has a horizontal vector, you will be recurrent, and you've seen that argument now twice, once by Reynolds and once by me yesterday. Okay. So I think I'm out of time. Thank you very much for the opportunity to give these lectures. I really enjoyed doing it, and I've really enjoyed the conference in general, the nice people, and the other talks have been really fantastic. So thank you.
Are there any other questions or comments? If not, so let's thank Jon again